All right, let's start. Students are coming. Okay. Later. So let's continue from. Are you recording?
Yes.
Okay. Let's continue. We left yesterday. We were discussing about differences between different types of coordinated transmission methods. Of course, it applies also to reception similarly, which is easier because it's just based on receive beamforming, and it can be carried out based on the uplink pilots directly. So downlink is more demanding because we have to acquire the CSI from the same uplink measurements. Right, so we have these two extremes. Coherent multi-cell beamforming, all the users are served by all base stations. These are S equals these are K equals B. B includes all the base station indices. Then there's this other extreme where each user is served by only one base station. And there can be some freedom how to choose this base station at the cell edge. Also, not only based on the path loss, but also based on the instantaneous channel realization. It's more like a dynamic cell reselection approach. We will see some numerical examples how much gains we can get from such scenario, and then any combination of these two. So we can have overlapping subsets of base stations. Right? We can have one user served by base stations, say 1 and 2, another user served by base stations 2 and 3, and so forth. So these are overlapping active sets. Actually, it's somewhat similar to soft handover in 3G, that the user can be connected to multiple base stations at once. But of course, soft handover is not related to multi-antenna process. Okay, all right. This is just another reminder of the optimization, general optimization objective. We can present an optimization problem in a general form as a function. Let's say for maximization, this function should be preferably concave to be easily be able to handle easily. And then this function is it depends on these variables gamma. Because gamma can be fixed, then we will have a maximization of the minus power, minimizing the power. So now the SINR expression is somewhat different than what we had in slide 5. We have now the receive beamformers per stream, and then the possibility to serve each user by multiple base stations. All right, and then we have this per base station power constant, and we can obviously have per antenna power constant. Okay, and add whatever quality of service constraint. Now, since we have multi-antenna receiver, each user can support multiple streams. So instead of, let's say, minimum maximum SINR constraints, we can have also minimum rate constraints. Right? That we could have we could impose there for a specific user. We could have a, let's say, minimum rate. So the rate should be always larger or equal to the sum over the streams that belong to, let's say, set of streams that belong to user K, log 1 plus gamma A, right? So the user has, let's say, 4 antennas. It can be allocated up to 4 streams, right? Assuming that the transmitter has more antennas for transmitters. So we can impose this type of additional quality of service constraints there as well, which can be handled not directly, but after some relaxations. Okay, just like before, we can have we can express these functions now. The function of stream index in the single antenna case was directly at the user index. So we can have multiple of these stream indexes belonging to a certain user. So there's a full flexibility in principle to allocate streams across different users. Okay. Similar as before. Okay. So as we know, these SINRs, they depend on two sets of beamformers: transmit beamformers, receive beamformers. The receive beamformer is usually simple. Whatever function, objective function you plug in here, if you write a Lagrangian and differentiate that with respect to this WS, you can see that actually the constraints don't depend on WS. This is the transmit power constraint. So it's unconstrained. Okay. Yeah, it becomes an unconstrained because the objective depends on the SINR. So basically, when you solve that, the optimum solution always is a MMSC receiver or scaled MMSC receiver, right? Always. The transmitter side optimization is more complicated. Okay, so generally you cannot solve these problems jointly with respect to receive and transmit beamformers. But since there's no cooperation between users, the optimization at the user end, the receiver becomes decoupled, right? So they can be done independently, meaning that the MMSC receiver can be computed ideally in practice at the user based on the, let's say, message downlink recorded pilots. This is something we will discuss later on. So this leads to typically iterative procedures, kind of alternating optimization, where the transmitters and receivers are optimized separately in an iterative manner. So we can start with, for example, with some feasible transmit beamformers, random match filters, whatsoever, scale them in a way that transmit power constraints are met, and then compute the receive beamformers. Those are the scaled MMSC receivers. So you can safely use MMSC receiver at that step. And then for the receive beamformers, for fixed receive beamformers, then you compute the transmit beamformers. When you look at this SINR formula, when you fix the receive beamformers, this becomes a vector, right? So then we are back to the slide set 5, like an equivalent single antenna unit, right? The receivers are fixed. This product becomes a vector, let's say H bar equivalent channel, and then you can use the tricks that we discussed in the previous slide set for max min SINR, max rate, whatsoever. Okay. Due to the receive beamformer step, we can quite often, for example, if we think about sum rate maximization, the natural way of solving this is via weighted MSE minimization. This is something that we will discuss towards the end of this slide set, and that leads to kind of practical signaling schemes, how to optimize these beamformers based on pilot exchange, how to implement this alternating optimization by exchanging pilots between transmitter and receivers, bidirectional trading. This is something something that I have now included in the slideshow, which is now actually available in the module. There might be some minor changes left, but I think this is the content that we will cover during this remaining time. Okay. All right, so let's have a quick look at some numerical examples. This is some old conference paper, basically comparing correlated versus coordinated beamforming in a simple setup with single antenna receivers and just 2 base stations serving a limited number of users. Okay. All right, so this is a bit of repetition. Coordinated single cell beamforming. Each user served by a single base station. How to choose this base station? Typically, if we ignore the fast fading component, you just allocate each user the strongest, I mean the closest base station, or the base station with the smallest path loss or largest path gain. Right? This is a path gain actually, so choose the maximum, which usually corresponds to the closest base station, at least in kind of the field scenario. Of course, in the urban environment, you might have kind of street tunnels and so forth that complicates the assignment procedure. Okay, but now if we have users close to the base stage, close to the cell edge, right? The path loss from different base stations is more or less the same. Right? Then we can have some extra gain by choosing the instantaneously serving base station based on the instantaneous channel. Right? So we could, if we have this user here at the cell edge, exactly, let's say the path gain is the same from this base station to that user and from this base station to this user. By switching the serving base station based on the instantaneous channel, we can actually benefit quite significantly, especially when the number of antennas is fairly small. Of course, when the number of antennas is large, we have some channel hardening happening, then the selection gain diminishes, right? The more antennas, the less selection gain, right? Especially in the IID case. Of course, in the other extreme, when we have line of sight, there's no fading either, so you don't get any selection gain. Okay, but in general, this is a combinatorial problem. It's a binary selection, right? So it means combinatorial problem, so you cannot handle it directly. Of course, you can have an exhaustive search. You go through all the combinations. For each fixed combination, you solve the problem, and then in the end, you choose the best. Right? Of course, exhaustive search is also doable if the number of antennas, the number of users is small, the number of combinations. But then we could actually get most of this selection gain by using some suboptimal allocation algorithms. Like in one of your homeworks, you have this greedy selection, like this projection method. That's a suboptimal greedy method, but it actually performs almost as well as a full search for some rate criteria. Okay, so we will actually look at some suboptimal allocation algorithms to compare them to this exhaustive search. Okay, this system setup is fairly simple, just to be able to characterize these gains as a function of simple system parameters. So we have 2 base stations, 2 to 4 users, 4 users in this particular case. And now we have one parameter. Okay, we have the path loss. We assume that these users are now divided into two groups. Right? One group served by this base station, or being closer to that base station, and another group being closer to this base station. Right? And then we have this alpha parameter that controls the distance between these two groups. When alpha is 1, these users are kind of overlapping, right? Exactly at the cell edge. When alpha increases, these users get closer to the base station, because we keep the SNR fixed. We keep the SNR, the receive SNR fixed at the receivers. So basically, when these users get closer, the path loss decreases, but then we decrease also the power to keep the SNR fixed. Okay, to be able to compare, to be able to plot the rates as a function of alpha, the distance between groups. Okay, you can imagine that the alpha equals 1. You get this is the most difficult case for the coordinated beamforming, because the interference is the strongest. The best case for the joint transmission, right? When alpha increases, becomes infinite, means that these two cells are completely isolated, then there's no difference between coordinated and coherent beamforming, as we will see. Okay, this is the beauty of this model. Okay, let's start with the SINR balancing. Okay, so we are trying to maximize the objective function here is maximize the minimum SINR across all users. Right? SINR balancing it comes from the fact that we can apply we can express it in an epigraph form. It's called this gamma 0. Right? And then we write the SINR H B K N B K divided by H K N B. Okay. This would be now. Okay. This is the way to. I think you have implemented this in one of the homeworks already for the single verification case, and this is subject to per base station power constraints. Right? Some over users that belong to the base station B. Over for all three. Okay. This type of optimization problem we are solving here. So we are finding a maximum common SINR that can be achieved by every user. At the optimal solution, every user has the same SINR. That's the common SINR. Or SINR balancing, right? We are balancing the SINR across all users. Because if there is any user with larger SINR at the optimal, we can of course decrease the power of that user and transfer that power to someone else to increase the common SINR further. So intuitively, at the optimal solution, the SINR is the same. So we have equality here, right? Okay, so the objective is the SINR balancing. We have these different cases: coherent multi-cell transmission and coordinated single cell, so coordinated beamforming, non-coordinated, that we just carry out the optimization independently at each base station, and then TDMA. TDMA that we avoid the intercell interference altogether. We take turns. One base station serves its own users, the other base station is silent, and so forth. Okay. So, and then now we are operating it at the very low received SNR level, 0 dB. We can see first of all that, so this is the case when we have isolated stations, right? There's no interference between base stations. All the schemes perform the same, except the TDMA, of course. TDMA we have the loss. We lose half of the rate in this case. Doesn't make sense to use TDMA in this case because we have anyways isolated cells. We can serve all the users in parallel. Okay. Now when we start bringing these users closer to each other, so we start on the case where alpha is infinity, these two cells are completely isolated. Now we start to bring these users closer and we see what happens. Okay. We start to actually get some gain from coherent beamforming because the beamformer size increases. Like instead of having just 2 antennas, we have two antennas to serve 2 users for each cell. Now we have 4 antennas to serve 4 users jointly. So we start to get some beamforming gain, which is quite significant in the coherent case. So when we go to the select scenario, so all the users are kind of overlapping, we get the highest gain. Now we have the coordinated scenario. Recall now that we are serving 4 users in parallel. So this is an interference limited scenario, right? For the coordinated beamforming case. Each base station has only 2 degrees of freedom. So it's serving its 2 users, but there's no degrees of freedom to null intercell interference, right? So we have upper bound for the SI, but we can still support. This is the sum rate, so meaning that if you divide this value by 4, the rate per user is less than 1 bit per second. Okay. But you can see actually that you can get significant selection gain here. So this is the case where the allocation is fixed based on the pathos. Right? No selection gain. But when you allow here a selection, this is the exhaustive search. You go through all the combinations. That, okay, allocate 1 and 2 to base station 1, 3 and 4 to base station 2. You know, you go through all the combinations and choose the best. This is the gain you get from this. Allocation, dynamic allocation. Percentage-wise, it's fairly significant, 50%. And then we have these heuristic cases. This is actually a very simple allocation. We choose the beamformers to be match filters. So the beamformers for the selection algorithm are just choose to be normalized and then dividing the power equally across the users that are allocated to that base station. Okay, so this is the beamformer match filter basically with equal power loading. But we now plug in. So this is for the coordinated beamforming. We plug in the SINR and we just compute. So for each allocation, we compute the SINRs. So we try all these allocations for each, and we just plug in. It's a simple because we can just try different allocations for this given heuristic beamformers, and we just choose the best combination of SINRs out of these all combinations. It's much faster than rerunning the optimization as many times as you have combinations. Okay, and you can see that you get almost the same performance as the exhaustive search. Okay, this is the case when you just choose based on the norm, that you don't try any spatial compatibility. Here in this case, you try to find the best possible combinations that gives you the highest SI. So there's a test of spatial compatibility. Okay. Now, even if we are interference limited, you get some gains from the optimal beamformer design. You find a good balance. Even though you cannot null the interference, you can still improve somewhat from the scenario where you do the optimization completely independently at each base station. The green one is that non-coordinated. You ignore the interference altogether. You just optimize the base station. One optimizes the beamformers for allocated users, so independent without considering the interference. Okay, this was the lowest SNR scenario. Now, the same scenario when we increase the SNR to 20 dB, 100-fold increase in the linear scale. Okay, you can see that, of course, the relative gain from the full virtual Mimo array is not as much as in the lowest SNR, because we are in the logarithmic region of the array. But the coordinated beamforming doesn't work at all, because we are interference limited, right? You're trying to serve 4 users at the cell edge, jointly having only 2 antennas at each base station, right? So it's interference limited. You can see that without the selection, the rate per user is exactly 1 bit per second, meaning that SINR is 1. Okay? You get some gain, well, quite significant gain, 50% gain almost by the selection, but it's not really useful because you are interference limited. Right? No matter how much you increase the power, the rate will not increase. Okay. And of course, the uncoordinated works even worse. Interestingly, the TDMA is now better than trying to serve all users at once. Okay, even though you get this loss of 50%, you still perform better than trying to serve all the users at once. So now here the base station state turns. Okay, now if we reduce the number of users to 2, meaning that both base stations have enough degrees of freedom to cancel suppress the interference. Now you could, of course, the number of combinations is far less. You can allocate all users to base station 1, all users to base station 2, user 1 to base station 1, user 2 to base station 2, or user 2 to base station 1, user 1 to base station 2. These are the combinations that you should go through. Therefore, the combination, the gain from the selection is of course reduced because you have less combinations. But the throughput is greatly increased. If you think about the rate per user here is 1 bit per second. Here is 6 bits per second, right? Because it's not interference limited, right? While still the uncoordinated case is interference limited, because you are ignoring the interference altogether. Okay. This is just another. One thing to notice here is that even with the perfect joint transmission, you get the numbers. Here with 2 users, you get 6 bits per. 8 bits, almost 8 bits per user. Right. Here you get 4.5 bits per user. The sum rate is increased from 16 to 18, so 4 users instead of 2 users. But the user-specific rate is decreased from 8 to 4.5. This is due to this max-min SIMR. It's quite, because it's absolute fairness, so it imposes from the system performance perspective, sum rate perspective, it's not very efficient, right? Now, if we allow max rate, so instead of maximizing the minimum of SINR, we maximize the rate across all users, you get a further increase in the sum rate. Now, how this rate is allocated over users can be anything. It could be that some of the users, especially in the low SNR, are not served at all, right? Because that's the sum rate optimal solution. Okay. But anyway, the same order here. The uncoordinated doesn't work. DMA, okay, doesn't work as well as the. So actually, what you can see here is that because the sum rate objective has this option to allocate zero SINR to some users. By default, even in the highly loaded case, when we have 4 users here, after running the sum rate maximization algorithm, there are only 2 users with positive SIN, right? That's why the rate here is not interference limited, like in the maximum SIN, where we enforce all users to be active, right? You get this one. We have 4 users. We try to maximize the common rate across all users. We are forcing all users to be served. So we are forcing an interference limited scenario. In the max rate case, where the objective is simply sum over all users, log 1 plus gamma k. At the cell edge, some of these gammas are 0. Right? You don't allocate any power to a certain user because that's better from the sum rate perspective. Okay? Because if you allocate now power to all users, you will be interference limited and the sum rate will decrease. Okay? This is the kind of main message of this figure. All right, let's move on to this distributed minimum power beamforming, which is also a topic of the final project of yours. So I recommend to read this paper. It's written 10 years ago, but it's quite fundamental, and I think it's fairly easy to read. Which just describes the details actually are the level of details that is included in the slides should be enough to implement the final project, but there's some more fine details available in the paper itself. And then we might actually ask you also to implement the same thing, but just using primal decomposition instead of dual decomposition. We'll see about that. Okay, so in 6.1 we define this complicated system model. We have the possibility to serve every user by multiple base stations, each user having multiple receive antennas, and each base station multiple transmit antennas. So now we simplify the model. This actually can handle also the coordinated, the coherent joint transmission case, like the partial when some of the users are not, the users are served by a subset of base stations. We could still decompose partially that processing. But anyway, for simplicity, we focus on this coordinated beamforming case when each user is served by one base station. Okay, and we have a fixed index. So we have a fixed assignment. User K is assigned to certain base station B based on path loss, for example. Okay, the system model from 6.1 is simplified to the receive signal. received signal consists of the desired signal. This is the stream, the data symbol allocated to user K, transmitted from the serving base station of user K to user K. Okay, so this could be user 1 and user 2. This is now the base station 1, base station 2. So the base station d sub k associated with user K is 1, right? And d sub k associated with user 2 is 2, okay, and so forth. So this would be hd sub k, well, h1 of 1. If we are focusing on user 1 here, this would be channel from base station 1 to user 1, and then the associated people. Okay, and then we have all the interference, either from intracell interference or intercell interference, right? From all other beams that are transmitted in this multicell network. Okay. This summation is now, we can write it over the user, because for each user we have a base station index, associated base station index, and a beamformer index. Right. So this stream, of course, if we have some core network here, of course the data, so D1 is directed to this base station and D2 to this base station, okay? And then D2 is recorded by M2 here and D2 recorded by M1 over here. So this is the model. The same, otherwise it's the same as with a single cell. If you compare this to the single cell case, the only difference is this B index here, right? In the single cell, this B index is the same for all users. So, coordinated minimum power beamforming, the same as in that. The formulation is almost the same as in the single cell case, but now we can write the summation over base stations and users that belong to a certain base. Of course, we can replace this simply by a summation over users as well. This is excellent, right? If users 1 and 2 are belonging to base station 1 and 3 and 4 are belonging to base station 2, this is the same as summing over users from 1 to 4. Okay, no difference. And now the SINR includes just the base station specific channels. And no matter, the interference can come from the same base station or whatever base station, whichever base station is serving the user I, which is causing interference to user K. Model is fairly simple, and this can be solved optimally. The same SOCP, you can just plug in the same SOCP implementation that you have, thus including now changing the indices here. If you look at the formulation, the same as in the single cell case, except that we have this base station specific indices here, and we can also handle the coherent case. If we allow joint transmission, if we allow, for example, let's say, if this base station is served by these two, so this user is served by these two base stations, and this user served by these two base stations, meaning that interference coming from here and interference coming from here, we can incorporate it into this model as well. So the SINR, you have the summation here. Now we need to add also this B index because we allow joint transmission. Right? So this transmit beam is now happening. This transmission is happening now from all base stations that belong to the active set or serving set of base station to user K, and similarly for the interference. So we can write that as an SOC constraint. So instead of single cell, for each user, we should sum up the contribution from all serving base stations, H, B, K, N, 1, to some B belong to base stations serving user capital K. Okay. Smaller equal to square root, and then again the summation over the serving base station. Still, we can assume that, assuming perfect synchronization across base stations and perfect carrier phase synchronization at the base station, we can assume that this summation is real value, right? So we can express that as an SOC. Okay, so this data is actually in the journal paper. If you can write that down. Okay, so far fairly straightforward. Okay, now, so this can be solved optimally in a centralized setting. So basically, we have a central controller that now each base station now can measure the channel, assuming full reciprocity, TDD, no error in the channel estimation. This base station now estimates all this HP, H1, K channels, and then forward this measurements to the central controller. Similarly, this base station measures all the channels, and the central controller has knowledge of all the channels, right? The channel knowledge is required. We need to know all the channels here to be able to compute these optimal beamformers. Okay. And we can actually solve this via the uplink downlink duality as well. No difference. Exactly the same. This channel indices just changes. You have to just incorporate this user-specific, base station-specific channels to this G matrix, or the uplink downlink. The uplink MMSC receivers are the same, but now the interference can come from users that are served by different cells. No difference. Actually, you can find that in this paper. This is the uplink downlink duality solution for the multi-cell scenario. Very straightforward. Okay, but now we are interested in a scenario where we don't have the centralized controller. Okay, we have local processing. We have a base station where the beamformers, we would like to compute those beamformers locally at the base station. There's a baseband that takes care of computation of those beamformers. For example, in this case, that we have these two users allocated to this base station and these two users allocated to this base station. Right? So this base station would like to compute the beamformers to these two users such that the interference caused towards these other cell users is properly managed. Right? think about scenarios that, okay, now if we have the TDD set up and each user here is allocated with a orthogonal pilot, which are known, right? So knowing those pilots from the uplink transmissions, pilot transmissions, of course, this user is a single antenna user. So these when users are communicating uplink towards this user, it's broadcasting, right? So that same transmission can be also heard by the base station, this base station. So especially at the cell edge, the estimation quality is more or less the same at both base stations. Okay. Of course, here we estimate perfect quality anyway, for simplicity, but we can also include some uncertainty here as well. Okay, so we can estimate locally this channel. And one obvious solution to control the interference, since we have now 4 antennas here, is just to project these transmissions to the null space of these vectors, right? We can do that. Of course, that's highly suboptimal in the low SNR, but that's possible. By forcing these transmit beams to be in the null space of this, we can control the interference. We can fully suppress the interference. This is very easy to do. You can just do the pseudo inverse. You just collect for base station 1. You collect all these channels H11, H12, H13, H14 into matrix H. This is the channel matrix of all these vectors, including both the desired users and interfered users. Okay, and then we just take a pseudo inverse of H and choose the first 2 columns or rows of the pseudo inverse to be the beamformers for users 1 and 2. That will automatically null the interference at users 3 and 4. Okay. Similarly, for base station 2, we can collect, H21, H22, H23, H24 into another matrix H2 measured at base station 2, and again take the pseudo inverse of that matrix and choose the last 2 columns or rows as beamformers, right? So this interference is fully cancelled. Okay. We should include this in the homework as well. But it's very, very easy, just a special case of the coordinated beamformer. So this is the simplest way of doing this. But it's it's highly suboptimal at lower level. So this is a simple ZF solution, completely null. Now we would like to find a balancing solution to allow some controlled intercell interference. These are the precoders in the adjacent cells accordingly. Okay. All right, some background. So by doing this distributed solution, we have a local beamformers designed just based on that local channel knowledge. But then we exchange some limited information between adjacent base stations. Basically, the information is related to how much interference this base station can cause to this user, these 2 users, and how much this base station can cause to these users. Another simple case is to fix interference levels. Okay, there's a pre-agreement that okay, this base station should not cause interference more than the noise level. Okay, at the receiver. And similarly, this is also something that could work okay in practice, and this is also something that we study numerically later on. So there are many different ways how to optimally decompose this problem. In this paper, we use dual decomposition, here primal decomposition, and in this paper, it's an extension of this one. They use the ADMM, alternating direction method multiplied. It's just a generalization of dual decomposition, adding some quadratic terms that speed up the convergence. Okay, we can currently always feasible solutions and so forth. Okay, let's start with the reformulation of the SINR. This is the key step for decoupling. So if you look at the SINR, from one serving, the serving base station perspective of user K, right? The SINR includes the beamformers also used by the interfering base stations, right? Which are not available by default because we have local design, right? We know only the beamformers that are designed for other users that are served by the same base station. So the first thing to do is that we separate intracell interference and intercell interference. Okay. So we pick here, this is the intracell interference. We pick here all the users that belong to the same base station, right? So this is the user set. This includes user indices by the base station that serves user K. Right? So it includes, if, for example, in this case, U1 includes 1 and 2, the U2 includes 3 and 4. Okay. So here, the interference for user, if this is user 1, the interference comes from intracell interference comes from user 2. Okay. And then we have intercell interference caused by users 3 and 4. Intercell from other cells, intracell from the same cell. Same cell, other cell. Okay. So we just collect now this intercell interference terms from all other base stations except the base station that is serving the desired user K. Right. This is the summation. Of course, in this simple example, when we have two base stations, this includes only B equals 2. Right. We have only one base station causing interference. So we would have only summation over users 3 and 4 here, right? 3 and 4 causing interference to user K. Okay. So interestingly, if we fix this term here, we can solve this locally, right? If this term is fixed to some, let's say, optimal value, we could simply do the local optimization of M1 and M2. Is clear? It just added to the noise value, and you just do the same SOC or uplink downlink duality base or whatsoever. Optimize it for fixed SINR. Okay. The complication here is that when you now, what we do here is that we now, to be able to handle this optimally, we introduce a new variable. It's called psi. What is it?
Psi.
Psi.
Or zeta.
Or whatever. Eta. No.
Z.
Z. Whatever. This letter, it's a new variable that corresponds to the intercell interference from base station B to user K. It's the total interference from base station B to user K. Okay. So we can now include it as, so making this gamma here. gamma k, the expression for the SINR. Now we have a variable of the intercell interference. This is just a quadratic term. Okay, we have a variable, the summation over all base stations, all interfering base stations, to use a k. There's a sum interference caused by base station B to use a k from all interfering base stations. Okay. To handle this, we have to relax. So we have an inequality here first, but we relax that to be able to handle it. So meaning that the interference from users that belong to base station B is the sum interference to user K, any user K, is upper bounded by this variable. At the optimal, it will be an equality. So this is actually, this can be written as a SOC directly. The SINR can be written as an SOC. So we have still a convex optimization problem, right? It has exactly the same solution as the original, right? It's just a free formula because at the optimal solution, this holds with equality, so we can just plug that back into here and we're back to the original instead. Okay? There's no difference. It's exactly the same solution. We have just introduced now this interference variables. So the first step towards the this distributed solution is to fix these values, right? Or assuming that if they are fixed, the problem decouples, right? From the base station B perspective, we can assume that the interference caused by other base stations is limited by this value. It's known and fixed. And at the same time, we have to limit the interference that we cause to other users in the other cells to be below that fixed value. Okay, so this problem decouples completely. So we can solve that individually at each base station for fixed interference terms. This is the first step towards this decomposition. Okay. All right. Before we go to the dual decomposition, let's have a 5-minute break. Get back, say, 18 past. All right. Okay. So recall that now if we fix these interference levels to optimal values or whatever values, both at the interference constraints and the SINI expressions, the problem decouples completely. And if these are optimal values somehow known beforehand, we have an optimal solution. Okay. Of course, these values depend on the beamformers, depends on the channels and so forth. So the optimal values are not known in advance, right? So how to find these optimal values along with finding these local solutions for the beamformers. So now we can come up with iterative solution using optimization and decomposition. And here we choose one particular way to decompose, dual decomposition of additional equality constraints. Okay. So the first thing what we do here is that we take local copies for each interference constraint. But these are should be globally known, right? We take a local copy both at the serving base station and the interfering base station, right? You see that this term depends on two indices, B and K. So it couples the user K, which is served by base station B of K, and the serving base station, the interfering base station itself. Right? We just take two local copies of this. They are equal, no problem, and we can apply them locally, and that's fine. Okay, so just to find the local consensus of these values, we first apply this partial relaxation. So what we do here is that we just apply partial Lagrangian relaxation of this equality constraint here. So we plug it into the objective and associate that with a certain dual variable. Okay. And that happens here. Right? So we have the original objective, which is now still decentralized. This is still the centralized problem, right? The summation over all the variables are all beamformers or all users. Still, we need centralized knowledge of all HPK to be or able to compute n sub k for all users, even with this equality constraint. Equality constraint is just that it's redundant here. Of course, it can be handled in the global optimizer, but it's redundant. So what we do here is that now we relax this one into the objective, but we form a partial Lagrangian as that consists of the primal variables n and this interference constraint. Now we have included all these base station specific values into a base station specific vector, right? So this includes all values for all users from one base to base station 1 to base station capital B, right? So these are the local copies. These are the variables, local copies. Include the local copies of the interference terms. And these are the dual variables associated with the local copies. This equality constant. So you can see that we have altogether, we have all these, how many constraints we have? K times this equals all K times B minus, but it includes only the interfering terms, right? Of course, not for the intercell interference terms, not the intracell interference terms.
But KB term should be there because each SNR is associated with some zeta.
Sorry?
Each SNR that associated with some zeta BK.
Yes, sure.
So we should have that many number of zeta BKs.
Sure. We have for every user,
Yeah.
from every interfering base station. Okay. Intercell interference for every user multiplied by the number of interfering base stations, but not including the intracell. You can compute that. Right?
Why we want these two copies to equal?
Because we want to find okay, this becomes clear later on when we start, because when we come up with the iterative algorithm. At the optimal, we want this to be equal, right? To have, if these are not equal, then this value used here, it will be different than in the SINR, and it's not feasible, right? We might be causing too much interference, while if the local copies are not the same, then we have infeasibility, right? Then it's possible that the interfering base station is causing more interference that is assumed at the serving base station, right? So we have to have this global consensus in the end. So this is the first step to lead to this distributed algorithm. Okay, hopefully it becomes more clear later on. Okay, so now here, actually the length of it's given in the journal paper. I don't remember by heart, but it includes the intercell interference terms for each user. Okay, k times something.
So what happens to the other two constraints?
They're still there. We will get into that. Okay, we just focus on the objective, right? So now this is just modifying this partial Lagrangian. Okay, if we write the whole, we can of course write the whole Lagrangian, right? We can write the whole Lagrangian without this, and it leads to this uplink downlink. Well, this Lagrange dual method that we discussed in slide set 5, right? But it's still centralized. But certainly we can solve this using the Lagrange duality directly, but the solution would be still centralized. The beamformers we would be able to compute locally, but when we convert that back to the primal domain, we need to know this G matrix, which is a global. Right? We would need to have that global knowledge there to compute the primal values. Anyways, these details are included in this paper, right? But this is still a centralized algorithm in the end. And the other problem here is that if you want to do this iteratively, the intermediate solutions are not feasible. Okay, so now we just handle first this maybe as with any Lagrangian, now with the partial Lagrangian to come up with the dual optimization problem. We first write the dual function, but now only in terms of this relaxed constraint, right? Only in terms of the Lagrangian that correspond to this consistency constraint. Okay, and the minimum value of the partial Lagrangian given this dual variable is written like this, right? Minimizing for given dual variable, find a solution, minimum solution of with respect to the primal variables mk. This step is also there for the global Lagrangian, right? You find the beamformer expressions and the dual problem corresponding to the SINR constraints, this lambda values and so forth. Right? Maybe you want to go back to this slide 5 to remind how that goes. Now we just focus on finding the dual problem for this dual variables that we have associated with the partial Lagrangian. Okay, so now back to your question. What happens to these original constraints? Now we have a new problem when we fix these dual variables. We have these two values that we have only those. We collect now all those values that correspond to this B index because these are the local copies of this intercell interference terms that are now weighted by this fixed dual variables. So now we have actually a local problem which can be solved locally at the base station B. Right? So you have recall that we have these interference terms here from interfering base stations causing interference to user K, but these are the local copies of these interference terms which are optimized. These are optimized and variables. And then we have in the interference term that we associate with that our own beamformers from that base station B are causing to other cell users. Okay, and these are still in the local copies. So they can be very wrong, right? We don't have, in the beginning, when we start tuning these weights, we don't have any yet consistency, right? When we solve this for a fixed value, when we look at these local copies, we don't have this equality here. The idea is now that the basic idea is that now we start tuning these dual variables. These are the weights. You know, when you increase the weight, when you increase this weight corresponding to one interference term here, it's meaning that you want to minimize that value because you're minimizing this objective, some objective here, right? By increasing this linear, the weight corresponding to that linear term here, you start to decrease that term in the objective, right? So this is kind of indirectly, now by changing these dual variables in different base stations in an appropriate manner, you can start pushing those local copies of these interference terms towards the consistency, right? This is the basic idea. And that follows directly from the decomposition. So this is locally solved. You get these beamformers and the interference values, okay? Now what you can do is that you can ask the interference base station to report those local copies of the interference terms that you have in your own base station, right? You just ask all those base stations, okay, please report, and then you send back your own versions. Okay, so you exchange these local copies, and the massive problem when we maximize this partially relaxed dual problem with respect to this Lagrangian that are associated with this consistency constraints. Basically, you just take you differentiate the Lagrangian with respect to these dual variables. What is left here, that's the subgradient. That's subgradient of Lagrangian with respect to this dual variable. What you get here is this. This is the subgradient. It's simply the difference, right? It makes sense. Like we have these two values local copies. If they are not the same, that leads to an update of that corresponding dual variable that will push the solutions towards consistency, right? So now what you do is that you just iterate, because it's a subgradient, you have to add here a fixed step size. You just iteratively, you solve it for fixed dual variables, you exchange these local values, you update the dual variables that will push these local copies towards consistency, right? After iterating enough, in the end, this difference goes to 0, and there's no update of the dual variables, okay? And then you have the globally optimal solution, providing that the step size is small enough, right? Because it's a subgradient, the monotonicity cannot be guaranteed here. But actually here, in the numerical simulations, we notice that even for relatively large values of step size, seem to be always monotonic for some reason. So it cannot be guaranteed to be monotonic. So now one important step is that since we have exchanged, the serving base station sends its value to the interfering base station sends it to the serving base station. So both base stations have the same knowledge now. So they can simply take an average of those values, and then we have a intermediate global consensus. And we can use these average values to solve the original problem, and we have a feasible solution. Okay. Even during the iteration, when we exchange these by solving this once more for these fixed values that are just average of the local copies, we can get a feasible solution. Right? We can be sure that the other users, other base stations that are causing interference do not cause more interference than the local knowledge that I have based on this average. Okay, so this provides us intermediate feasible solutions when we iterate. This is very important in practice when we apply that to time correlated phase therapy. Okay, perhaps you need to read this a bit more in detail in the journal and maybe the slides themselves, and when you start implementing this in MATLAB, it should become clear. Okay, let's consider a simple scenario. We have 4 users, more or less at the cell edge. We can again control the importance, the significance of the interference, just using this the same alpha parameter. Right? Recall that we have these 2 users are served by this basis, and these 2 users are served by this basis, and we can control this group separation by using the same alpha parameter. You know how close this alpha is 1, they are exactly on the cell edge. Alpha is large, they are well separated, right? The importance of intercell control becomes less important. It becomes less important to control interference. Okay, so the local problem for users 1 and 2 from base station 1 is to find the best possible beamformers to minimize the power subject to interference constraints to these 2 users. Okay, and similarly, this base station minimize the power, find the minimum power beamformers that satisfy the SIN constraints while also controlling the interference that we cause to the other cell users. Okay, and now what we exchange here is that we have these 4 interference terms. Okay, so in total 8 interference terms, because we have a local copy of interference terms. So we can see that we have interference from base station 1 to user 3, and we have the local copy of that, because this is the local copy that we have to take into account in the SINR formula. This is the local copy that we take into account when we limit the interference. Okay, if they are equal, then we have feasible solution. If they are not equal, not feasible, right? So for each interference term, we have a copy, serving base station and interfering base station. It's a simple scenario because we have the 2 base stations. It gets a bit more complicated when we have more base stations, more users. But for each interference term, there are 2 copies. Each interference term couples exactly 2 base stations. Okay, that's a nice thing. You only need to exchange these terms between 2 base stations. Okay, so you exchange these, you can intermediate values, you can compute at both base stations, you can compute the difference, the same difference. The sign is different. If one is larger than other here, it's smaller here, right? The sign changes, so they actually update the update of dual variables go to opposite directions, which makes sense, right? Okay. Again, the same model as earlier. Okay, right. We still have this alpha parameter here controlling the separation. 4 users, 4 transmit antennas. So we could, in principle, serve all users by 1 base station as well. Okay, it would be somewhat. Convergence. Now what we do is that we have the optimal solution, giving certain value, the centralized solution. Now when we start iterating, let's see first the 0 dB SNR. This is the difference between the sum power for the feasible case when we use the average interference terms at both base stations. So here's the difference. The difference is quite large here at the beginning. When it quickly starts decreasing, here the difference is already 1%. In terms of power, that's nothing, right? We could already stop here, and it's a very minimal impact in the power. Right? So you can see that this converges very quickly in 5 iterations, even it's upgraded. Okay. For the higher SINR, it takes a bit longer. The higher the SINR, the more it takes. Why is it? What was that? Yes, the interference levels, the optimal interference levels start to approach 0, right? That's why if you use the same step size, also the updates are very small at once. So it slows down the convergence. You could compensate that by increasing the step size. Here is the same step size for both cases. Okay. But it converges, okay, in 20 iterations to this 10%, 1% error in the objective. Okay, some results first for the block fading. This is the required power for 0 dB SINR target. This is plotting as a function of alpha. Now if we have a completely separated setup, all the these optimized scenarios perform the same. We have also included this coherent transmission there as a reference case. Then there is zero forcing. Two types of zero forcing. We can just use this solution, right? Forcing every. Also, the intracell plus intercell interference to be 0. This is the solution. It requires how many dB more? 12 dB more power, right? Highly suboptimal. More than 10 times more power. Then we have an intermediate solution where we impose zero constraint only for the intercell interference. Right, that decouples already, but then we optimize the intracell interference. That's still an SOC, or can be optimized. Can be found optimal. And then this is the optimized. Of course, the zero force. The one thing to notice is that the zero forcing solution does not depend on the separation, because you're strictly forcing the interference to 0, so this path loss does not matter. Of course, the interference here is approaches to 0, the zero forcing solution is extremely stupid, right? In fact, when you do the user selection, optimal user selection here, cell edge. What was this? Okay, I think it's just going through the combinations. Then you get already significant gain. You check the spatial compatibility. The algorithm is in the paper. I don't remember now by heart. This is constant allocation. This is doing some spatial compatibility. Which users should be allocated to which base state. So that when you do that, the difference with the optimal, the relative difference decreases. Okay. So here we have this optimal coordinated beamforming. We can simplify that by we can have a per base station power constraint, per base station interference constraint, or just a single interference. So we just find just a single value that is common for all, and it still performs quite okay in the single in this small. So these are just to reuse the backhaul exchange further, right? So here we exchange just less terms. We assume that this term is the same for a subgroup of users. Okay, more details in the paper. In the higher SNR, obviously the difference to zero forcing decreases because the optimal solution approaches zero forcing in the higher SNR, right? The interference terms gets closer and closer to zero at the cell. Obviously, when the distance increases, you know, imposing this zero forcing, strict zero forcing becomes stupid, right? And then we start again gaining a lot. The difference between pure zero forcing and interference, the optimal interference control increases. Okay, but here in the higher SNR, the difference to the coherent case becomes quite significant. For the coherent case, you would need just 10% of the power that you would use at the for the coordinated beamform. Here, with the fixed allocation, by doing some dynamic user selection, gain still, or can be able to give you some calls. Okay, these are the block fading cases. More interestingly, because if we have a dynamic scenario, users are moving around, the channel is changing, but in a time correlated manner. Okay, so we would like to so now we have a scenario somewhat simplified because the path loss doesn't change. It's only the large scale fading that changes. Okay, we have these two base stations here. And then we have users now somewhere here at the cell edge. I think this is cell edge scenario. So now they are moving with certain speed. Okay. So now we have a kind of correlated fading process. So when this user moves a little bit, this complex values is changing. So you have, when you plot the amplitude per antenna, you have some kind of Rayleigh fading process. Okay, it is Rayleigh because it is uncorrelated. Okay, so for each fading state, we optimize the power to satisfy the SINR, right? So when you see that how this power, if you look at this ideal centralized case is the red curve. So because of the fading across all the users, the sum power varies to satisfy the SINR constraint at any given time. Okay. Of course, the more antennas we have, the less variation because there's averaging. More importantly, if we compare to the zero forcing, there's some significant, this is the exponential, the linear scale of plotted in that exponential axis. So there's significant power difference between, you know, sometimes there's some really high peaks, like this, at this point, the required power here is over 30 times more than in the optimal case, right? And so forth. And now when we use this decentralized method where for each frame we exchange just once these scalar variables and use the average value as a feasible beamformer. These are the blue instances here. You can see that just by exchanging these simple scalar values once per frame, we can follow the fading process, but still carry out local process. Doesn't require centralized process. Okay, this is the main practical advantage. So you can apply these subgradient updates of dual variables. So basically, we have never convergence because the channel changes, but we are able to follow the fading state. Right, the interference values keep changing along with the time due to the dynamic fading process, but they are able to follow very closely the optimal centralized design, right? This is the practical importance of this solution, right? Okay, there are some extensions. Yeah, if my student Harry graduated 5 years ago, we did quite some work extending, consider some cognitive radio scenarios. You can impose constraints, primary, secondary. Then we came up with this iterative algorithms to solve the local solutions. But then you need to, because you have these extra constraints, it's much more difficult to handle directly as the single cell case without constraints. When you impose constraints, the iterative algorithms become more complicated, and this constraint actually couples multiple dual variables, and you don't have this one-to-one solution as in the single cell case, where the lambdas can be found using these fixed point iterations. But since those lambdas need to satisfy multiple extra constraints, we need to use subgradients inside the each base station. But it can be still much faster to be solved than, let's say, SOCP. If you don't want to go for the like a full convergence, that we are fine with some little error, can be justified in practice. Then we can use this worst case, the same worst case design as we went through in the slide 5. Now we're applying it to the multi-cell scenario that's described here. Now we have this uncertainty now affecting the SINR plus the interference constraint. So we have to actually satisfy both SINR and interference constraints locally. So it makes the design somewhat complicated. Then with another student, Hossein, who graduated last year, we studied an interesting scenario where, like a massive Mimo setup, where these interference constraints can be approximated using random matrix theory. When the dimensions of the network become large, these scalars here, they become deterministic, right? And we can then apply those deterministic values of interference constraints to the finite cases, finite number of users and antennas, and get very accurate results without need to exchange the instantaneous realizations of these interference values. So we can find accurate approximations based on statistics only. Okay. All right. The last topic that I'm planning to cover on Tuesday is weighted sum rate maximization for multi-cell Mimo networks. And this is relying on this reformulation via weighted MSE minimization. This is a very practical approach to to do it. Sometimes, quite often, you don't need, you can ignore the weighted rate maximization and then just go directly to the weighted MSE minimization, right, for fixed weights, which works quite okay. So you don't have to actually, you can reduce the iteration. But I will go through this weighted sum rate maximization. It is general, but then the weighted sum MSE can be the practical solution that can be used and converges much faster. Okay, maybe just a couple of motivating slides before we quit. Continue on Tuesday. So again, we consider cellular Mimo setup, now multiple antennas at the receiver. For simplicity, we assume that the user to cell or user to base station association is done, right? This is for fixed association. So we have now a solution where the base stations have agreed that, okay, these two users should be served by this base station and these two users by this base station, right? So given this fixed association, we want to find the best beamformers applied both at the base stations and at each user to maximize the weighted sum rate maximization objective across all users, all streams. Okay, and possibly with user-specific rate constraints. I'm skipping that; it's a bit more complicated, but we can include also in the general setup. No problem. This problem can be proven to be NP-hard. First of all, the fact that we have this joint design of both receive and transmit beamformers. This is one that complicates. But even if for fixed receivers or even with single antenna, as we know this from slide set 5, the problem is non-convex, right? To the SINR. It can be proven to be NP-hard even for a single antenna case, right? The SINR objective. There are only, as we discussed, there are only few objectives that can be handled optimally in the single antenna case. The minimum power, maximum SINR, and that's about it. But even minimum power and max SINR, when we include multiple users and multiple antennas, cannot be solved optimally. It becomes non-convex because of this joint design of transmit and receive beamformers cannot be solved at once. So the focus here is computational complexity, a local design of beamformers based on local channel estimates, and then minimal backhaul signaling. Okay. All right, let's continue with the mathematical preliminaries on Tuesday. It basically extends from the information theory, theoretical approach that we already covered earlier during this course, but then we are now imposing this linear constraint and then splitting the transit covariance matrix into recorders, multi-rank recorders. Okay, let's continue on Tuesday.